Hello, welcome to lecture 28. This is a review lecture in the topic of integration. I have, as usual, collected a bunch of the useful facts that we need to know here, but we've been through this many times, so I'm not going to talk about them. I encourage you to just pause the video and try to read through them and maybe copy them down if you're taking notes, just to make sure that you understand and you remember what they are about. Indefinite versus definite integrals, area function, and then the fundamental theorem of calculus, the two forms of saying it, one involving the area function, the other involving antiderivatives. The second form being the one that's the most useful usually. And then finally U sub, both for indefinite and definite. Remember that for U sub, we do have the formula like this, but what's more important is the procedure, how it works, and it's described here in items. But yeah, we're gonna go through this in the problems. So I'm gonna flip the page. What I prepared for today is just a bunch of problems. I'm gonna solve as many as we can here, given the time for this video. And whatever is left will be given in recitation 14, which will be the last recitation. So here's the first one. This is one that's very similar to one that I was gonna originally give in one of the lectures. I think it was 24, 25. And I decided to leave it for later. So we have an integral to just calculate from -2 to 2. It's definite. What you have to think about when you look at this integral, you see inside here an expression that's called a linear expression of x, something of the form ax plus b. That's always a good candidate for u substitution. So we're going to do that. The only problem is that if we call that thing u, then we're going to have, when we do the change of variable, this x inside of the sign is going to become more complicated. But what you have to realize is that there's no reason to treat the two functions, the two pieces, together in the same integral. What you have to do here is split this integral into two separate ones. First of all, before doing your u substitution. So calculate this, just this first one, and then minus the other one with the sign. And now you're going to use u sub only in the first one. So let's see how that would go. If we call u 4 minus 3x, that means that du over dx, the derivative of u is minus 3. So we usually write this in symbols as du equals minus 3x. Now we don't see a minus 3x in this integral, we see just a dx. So we're going to introduce a minus 3, as well as divide by minus 3 to cancel it out. But remember, this is also a definite integral. There are endpoints, and we have to change those accordingly. We need to change those to their new values according to the u substitution. So it works like this. When x is equal to the, let's say, the lower endpoint minus 2, the corresponding u value would be, just look at the relationship between u and x, 4 minus 3 times x. 4 minus 3 times minus 2, that's 10. And when x is 2, u is going to be 4 minus 3 times 2, that's minus 2. So we need to change those. And okay, how does this work? Let me first of all move the 2 over 5 outside of the integral. Also, the constant 1 over minus 3 that I'm introducing in order to have the proper u substitution to work here. This minus 3 that I'm introducing here, because of the minus 3 dx that I want, is now being canceled with this other minus 3 outside. All right, so this is the change that has to be done in the first integral. And let's keep the second one the way it is. These are now two integrals that we can compute. Just replacing everything here. For the first one, you have minus 2 over 15 outside. And the integral is just u cubed du. All right, the 4 minus 3x is getting replaced with u. And the minus 3 dx, here it is just du. And okay, once again, just copying the second integral. Now we can just calculate these. Integral of u cubed with respect to u is the same thing as u fourth over 4. And that needs to be computed between the numbers 10 and minus 2. Minus. Integral of sine is minus cosine. The derivative of cosine would be minus sine. So when you're integrating just sine, that will give you minus cosine. Calculated between the endpoints here never changed. The u substitution only applied to the first integral. So between minus 2 and 2. Now just compute this. Minus 2 over 15 times minus 2 to the 4 divided by 4 minus 10 to the 4 divided by 4. And then there is a minus here, also a minus from the inside of parentheses, minus cosine applied to the number 2, minus cosine applied to the number minus 2. There's a lot of minuses there that I'm writing very carefully here so we can really understand what's going on. You know, this minus here is because of the difference between the two values. This minus is the same as in the function minus cosine, and this minus 2 is the number minus 2. So we can leave it like this. You can also check that this whole thing here is a 0. Cosine of minus 2 is the same thing as cosine of 2. Cosine is what's called an even function. So you can see that this simplifies down to 0. But you know, this would also have been just a correct answer here, unless they tell you to simplify as much as possible. Let's leave it like this. Move on to another problem. Okay, what is the area of the region of the plane above the parabola, this parabola, and below the x-axis? So what's going to happen in this problem is we have a parabola, y equals x squared minus 7x plus 10. And we can't see it yet, so we should probably draw it so we can visualize the area that we're trying to find. Because we want the region between this, above this parabola, and below the x-axis. So drawing a parabola is very easy once you discover where the zeros are. In this case, 2 or 5. And also from the fact that the first coefficient is positive, that means the parabola is concave up. So it is just a parabola that's pointing up and crosses the axis at the numbers 2 and 5. Now you can see what is the region that they're describing. The region above the parabola, but also below the x-axis. It should be only this part here. And now we can use integrals to describe this area. The area that we want, let me write something, and then we're going to need to add an extra minus sign in front of that. So what happens if you take the integral of the function between 2 and 5? You know, the integral represents exactly this, the area between the graph of the function and the x-axis. That is what the integral represents, except that sometimes it's a plus, sometimes it's a minus. In this case, this would be a minus, because this is an area that's below the axis. So if we want to find the actual value of the area, put another minus in front. So this is just because this region is below the axis. The integral itself would be negative. And if you add another minus in front, that gives you the positive value that you're looking for, because you're looking for the value of this area. Now just compute this. Minus, integrate the function, x cubed over 3 minus 7x squared over 2 plus 10x, calculated between the numbers 2 and 5. So I'm going to leave the minus outside, calculate at 5. Just plug in x equals 5. And now minus, calculate at 2. 8 over 3 minus 28 over 2 plus 20. And, you know, simplify this. I did this before, used a calculator. I'm not sure if this is going to be the exact answer because I could have a mistake, but this is really not what's important. Important is this is just a number and important to check that you're really getting a positive number. I guess that is important, because as we could have guessed from before, we needed this extra minus in front to get the area and not the integral. So that should be the answer. So I'm going to have a similar problem now. What is the area of the region bounded between the graphs of the following functions and the y-axis? So I'm giving you two functions, f and g. F is an exponential with a positive exponent. It's the one in red down here. G is an exponential that has a negative exponent in the x, as well as a number 10 just to cause a translation of the graph. So it's the blue graph. The two graphs and the y-axis, this piece, together they bound this kind of triangular region. It's not really a triangle because it has curved sides, but we're trying to find what is the area. Of course, we're going to use integrals to find this area, but this time, this is not just the area between one graph of a function and the x-axis. It's actually between two graphs of functions. So what we're going to do is subtract integrals for one minus the other. So before we do that, let's already at least figure out what are the endpoints of integration. What is this endpoint x here, where the two functions cross? That should be easy to find. When is f equal to g? So f is the function e to the 3x, g is the function e to the 10 minus 2x. When are two exponentials equal like this? If you take logs, that's the same as equating the two exponents. So now you have 5x equals 10, x equals 2. So we already know where they cross, where the two functions cross here, x equals 2. So the area that we want is actually equal to this. Let me write this down. Integral of g minus integral of f. Think about this. When you have the integral of g between 0 and 2, g is the blue graph, so you were talking about this entire area, this whole thing. And now you're subtracting the integral of f, which is the red function. So you're subtracting just the piece in white here, the piece that I'm describing now. When you do the subtraction, you're just left with the one that you want. And in general, this works like this. When you're looking at the area between the graphs of two functions, you're going to just subtract the larger function minus the smaller function. So this is what it is. We just have to calculate this, remembering that g was 10 minus 2x, f was e to the 3x. So those are integrals that we can find now, once again by U substitution. And they are once again definite integrals. They have endpoints. So when we do our U substitution here, we don't go back to the x variable in the end. We just find numbers. So let's do these two separately. Maybe I'm going to call one of them U and the other V, just to be clear. But the substitutions are all very straightforward here. The exponents are linear functions of x. So it's always a good idea to use that entire expression as your new variables. So let's see, if u is 10 minus 2x, then du dx is minus 2, meaning that du is minus 2 dx. So when we rewrite this integral, we're going to introduce another 1 over minus 2. And we need to figure out how the endpoints are going to change. If x is 0, then u is 10. And if x is 2, then u is 10 minus 2 times 2, 10 minus 4 is 6. So I'm just looking at the relationship between u and x to get the u values. All right. Now let's work with the other one. V equals 3x here. Use the exponent, the linear function of x, as your new variable. So dv dx is 3. That's just a derivative, which means dv is 3 dx. And when x is 0, the value of v is also 0. Look here. You're just multiplying by 3. When x is 2, v is 6. Okay. So what do we do now? We just go back to the integrals, replace them with what, using all this information. The first one is going to become an integral from, it was from 0 to 2, and now it's going to be from 10 to 6. Integral from 10 to 6. Remember that there's a -2 that I'm going to introduce here, so I'm also dividing by -2 outside. The function is e to the u, and because of the -2 that I introduced, I'm allowed to write du. So yeah, this is the transformation of the first integral. Do the same thing for the second integral. I forgot to write the 6 here. Okay. So the second integral will go from 0 to 6. The extra number that I need to introduce is a 1/3 e to the v dv. Now just calculate these. So 1/-2 is the same thing as -1/2. Integral of e to the u is the same thing as e to the u. The integral of the exponential function is itself. And then the other one, -1/3 e to the v between 0 and 6. Now just calculate all of this. -1/2 e to the 6 minus e to the 10. Notice this is a positive number as we expected. Both of these integrals represent positive numbers because they were integrals of positive functions. So this difference is obviously negative, but then there's another negative outside, which makes this positive. It's always good to check things like that. And then -1/3. Here's e to the 6 minus e to the 0, which is 1. I'm not going to simplify this. There's really not much that we can do other than replace e to the 0 with 1. But whatever, this is just a number. If you want to get your calculator out just to see what this is, I'm not going to do that, but just check that this is a positive number because it should represent an area. That could be a good idea to check. But all right, I'm going to move on to another problem. Problem, one of the two functions of x below makes no sense. Identify it, and then calculate the x derivative of the other one. So look at these expressions. The difference is in the variable of integration. It's called x in the first one, and it's called t in the second. One of them doesn't make sense. Which one doesn't make sense is f. F doesn't make sense. The reason is that the variable of integration x is used outside of the integral. That's never allowed. Remember that the variable of integration, it's the thing that goes here in the d, which indicates what it is, and it appears inside in this function. That's just a dummy variable. It can be changed to anything else, but other locations, even the endpoints, they are considered to be outside of the integral. They cannot include that dummy variable. That variable only exists inside. So the fact that the x exists up here, for example, is already a problem. That's why this initial function f here really doesn't mean anything. And the g is the one that is meaningful. So let's do this other part of the problem. Calculate the x derivative of the other one. So calculate g prime. We want to find g prime now. So how does this work? This is going to be an example of the first form of the fundamental theorem, where you have a function of x, where this x appears here and here, in the endpoints of integration. Meanwhile, the function being integrated is just some other function without x in it. So what is the idea? Remember what the first form says. If you have an area function, which means you have a number down here and just x up there, then we know how to find the integral, the derivative of that. It is just the function that's inside. But what we have here is two situations that usually happen. First of all, we have the variable in both locations, not just above and below, and not just above, sorry. And then second is the variable is not alone. It's not like we have just x in here. We have a function of x, sine x, as well as down here. So what do we do? Because we have functions in both endpoints, what we want to do is split this up. You choose some number. Let's choose, for example, the number 0. It really doesn't matter as long as it's a number that's in the domain of the function. Okay, so what is the, yeah, like this is a good way to write this. So if you want to integrate from e to the x to sine x, you can do it by integrating only up to 0, and then from there to sine. Doesn't really matter which one is larger or smaller. Like e to the x is always going to be larger than 0. So this integral is written in an unusual order, but that really does not matter. The integral always has this property. If you want to go from a to b, you can stop somewhere and then go from there to b. That's the property that we're using here, because now this splits up as two area functions. If we at least rewrite the second one so that the x part is on the top and not the bottom. So now you have a minus sign outside because you're switching the endpoints. All right, so I changed this plus to a minus because I switched these endpoints, 0 to e to the x now. Okay, so the two expressions being subtracted here, they're very similar. The only difference is what's written on the top, sine x versus e to the x. They are examples of area functions, but with something inside. Namely, if you call area function this one that goes from 0 to x, area function always goes from a number to x, then the g function, the way that we just wrote it up there, is area of sine x minus area of e to the x. That's the expression that we have, the g function, and now we want to find g prime. What is the property of the area function? The derivative is the function inside of the integral calculated at the x. This is the first form of the fundamental theorem of calculus. Just try to always remember this. When you have the area function with a number and x, the derivative of that is always the function inside, 1 minus t squared, but calculated at this location x that you're doing. So we're going to use this formula. We know what a prime is, the function a prime. Now we just want to use that to calculate g prime. What you have to remember is that you're going to need the chain rule to find the derivative of this expression with respect to x. So I'm going to write the chain rule for you here. A prime of sine x times cosine x minus a prime of e to the x times derivative of e to the x, which is e to the x. That's the chain rule. And now you just replace, instead of a prime of something, you have the formula for the a prime function right there. A prime of sine, for example, would be square root of 1 minus sine squared. A prime of e to the x, square root of 1 minus e to the x squared, which is e to the 2x. And that's your final answer. There are simplifications once again. 1 minus sine squared is cosine squared, for example, but let's not go there. We don't need to. All right, so the main thing to remember here is that whenever you have an integral where you see functions of x on the endpoints, like we just had here, you just know that you're going to need this first form of the fundamental theorem of calculus, but you need to rewrite the function using the area function like that so you can see that it's a composite function. And then you can take the derivative using the chain rule. Very good. Now this is a u sub problem with indefinite integral. There are no numbers here. Compute this crazy integral Suggestion, use u equals e to the x more than once. Let's see what this means. Just a quick reminder that when you have number raised to number raised to number, what that means, what does that mean? Is it equal to like a to the b to the c, or is it a to the b to the c? Which one is it? It's the second one. Just try to remember that towers of powers without any parentheses in them, you always compute them from the top to the bottom. So, okay, we have this integral. They're telling us try to use u equals e to the x. So let's do that. Du dx, the derivative, is e to the x, which means du equals e to the x dx. So what are we going to do with that? Go back to the original function. We see e to the x here, that we can change that to u. We also see it here. This is also a u. And I'm not going to call this e to the x u. I'm not going to do that, although we could, because what's going to be more useful for us is the fact that this whole thing is du. E to the x dx is the same thing as du, as we just learned. So when you do that substitution, you just get e to the u, e to the u, du. Just color coding this so you can see the change that happened. Okay, now we have this integral in u, which is still not very user-friendly, but it's simplified a little. How about we do this, the same change using the exponential function they said more than once. How about we try v equals e to the u? Let's see what would happen. dv du is also e to the u, which means dv is e to the u du. So once again, we're just going to use this entire expression, u to the u du, change that into dv, and also change this e to the u to v. What happens now? E to the v dv. This is one that we know how to find. What is the integral of e to the v? Just e to the v. I don't need to add a plus c yet because that has to be done only in the end. It's fine if you don't, but it's also fine if you do. Because what do we have to do now? This is not the final answer yet. This is a function of v, and we want it as a function of x. So you now go back through your substitutions. First, v is e to the u. So replace it. And then u was e to the x. So also replace that. And now is the time when you have to add the plus c because this is indefinite. But this should be your final answer. To check that this is correct, you take this function that you just found, e to the e to the e to the x, calculate a derivative. Because of repeated chain rule, you're actually going to get the original function that appears in the integral. So you can check that this is right. All right, this was one that I gave this example before in class, where this was given as two separate items using the substitution u equals x plus 1, which we did. And now they said, try to use the substitution u equals square root of x plus 1. And I said, let's skip this. I'll do it later. I encourage you to try first, encouraged at that time. And now I want to check that you did it correctly. So let's solve this. So what's going to happen? We're going to use the substitution u equals square root of x plus 1. Let's find du dx. It's really not that difficult. You just have to take the derivative of square root of x plus 1. By chain rule, the derivative of the square root is 1 over 2 times the square root. And the derivative of the inner function x plus 1 is equal to 1. That's why I have this times 1 here. So now write this as an equation between the differentials. Du is equal to dx over 2 root x plus 1. Okay, so we don't have this over 2 in the function. We do have this dx over square root, which appears here. We just don't have the over 2, so I'm going to go ahead and introduce a 2 outside. So I can also have a 2 in the denominator like this. And you see that I'm writing the square root part together with the dx part, because I now I know that that's going to be useful for us. That's going to be our du. But then we have this x inside left. We don't have, in the function that's left in this x part, we don't have anything like this, like the square root of x plus 1, which is often the case. The function often has the thing that you call u in it. This one doesn't. So somehow we need to substitute, to change this x into something involving only u. That's the type of situation where you also need to go back here to the relation between u and x and find the inverse relation, which is, in other words, solve for x in terms of u, which is what I'm doing here. Just take the square and subtract 1. This is x in terms of u. This is going to be useful for you because you want to use that to replace x's in the integral with this new expression, u squared minus 1. But this other part here is what we're going to replace with du. So you just have to recognize where each one of these pieces came from, what is the useful substitution to do for each one. Because, for example, you might say, there's an x here. Can I change that into u squared minus 1? Yes, you can. It is correct. It's just not going to be very useful for you because you want to use this whole square root of x plus 1 together with the x, together with the 2. You want to use that whole thing and change that into du. Right? So just because you see an x there doesn't mean you're going to use this inverse substitution here, although you do want to use it for this x. So let's carry this out. 2 integral u squared minus 1 du. Blue times red. Now this is a very easy integral to perform. 2 times u cubed over 3 minus u. There's no between. This is indefinite. So technically there's a plus c here, but we don't do that yet because we go back to the x variable first. So 2 times, let's see, u was equal to square root of x plus 1. So you're going to replace that with this. And that's your final answer. I forgot the parentheses for the number 2 multiplying the 2 functions. You can also write this slightly differently, like 2/3 x plus 1 to the 3/2, because it's the raising to a cube and then also taking a square root that is raising to 3/2. And here minus 2x plus 1 to the 1/2. So like if you plug this into a computer program, they will probably give you this answer in this format. I just want you to be able to recognize it's the same thing. And also go back to when we did this in class, whenever we were talking about the u sub, this is the answer that we got using the other suggested u sub, u equals x plus 1. So just to compare that, they are the same answer. Okay, moving on. IVP. IVPs are something that we talked way back, more than a month ago. We talked about them. Remember that IVP is just when you're trying to find a function, you're given its derivative. This is called the differential equation. And you're also given the initial condition, the value of the function at one specific point. And now you want to find it. U sub can also be used in IVP problems because you know that the first step to solve an IVP is to take the indefinite integral of the differential equation. If f prime is the function x over x plus 2, then f is the indefinite integral of that function. Let's find this first. How do we do this? When you look at this integral, there is no simplification that you can do here. It's not like you can split this as x over x plus x over 2. Don't do that. Fractions don't split in the denominator like this. So what is going to be a useful substitution for you is u equals x plus 2. because if you do that, first of all, it is just a linear substitution, so it always does something for you. But if you do that, you're gonna have just one number in the denominator and not a sum anymore. And that's why this is useful. So du dx is 1, du is equal to dx. We can simply change this dx into du very easily. This x plus 2 in the denominator will be changed into u. Also easy, but what do we do with the x above? Well, this is a case where you need to know the reverse change. X is equal to u minus 2. You change that, you use that accordingly. Right, so just like the example before. And now it is possible to split this up into two separate integrals, u over u minus 2 over u. In other words, 1 minus 2 over u du. Fractions do split up in sums like this when the sum is in the numerator, not denominator. How do we calculate this integral now? Integral of 1 is u. Integral of 1 over u is ln of absolute value of u. And you have a minus 2 multiplying that function. Now you go back to the original expression. In terms of x, u is equal to x plus 2. And there's a plus c because this is indefinite. That is the solution to the differential equation. F is equal to this function, but we don't know the c yet. We can find the c now from the initial condition. F of minus 1 is supposed to be 3. So 3 is supposed to be what you get in this expression when you plug in x equals minus 1, which is what I'm doing here. So what happens? 3 is equal to 2 minus 1 is 1. ln of 1 is 0. So there is no ln part here. 3 is 1 plus c, c is 2. Now that you just found c, go back into the function that you found up there, plug that into there, and you have f of x. X plus 2 minus 2 ln of absolute value of x plus 2 plus c, which is 2. You can combine these plus 2's now and make a plus 4. That's an easy enough simplification. But yeah, this is supposed to be a function. You can check now, like plug in x equals minus 1, see that you get a 3, you really should, and then calculate the derivative of that function, see that you get this expression. Those are little checks that you can try if you have time. Next example, this is also one that I mentioned in class, at least the item A, in one of the lectures, and I said, let's leave it for later. So first of all, they want us to compute indefinite integrals of sine square and of cosine square using these identities, which by the way are true identities. For sine and cosine squared, they can always be written in terms of cosine of 2x. This is not a typo, this is cosine here for both, even though there's a sine in one, cosine in the other. The formulas are correct. Okay, so when you look at the integral of, let's say, sine square, of course, you don't know of any function whose derivative is sine square off the top of your head. And also there is no easy u substitution there. No simple function that you see, like the sine function, maybe u equals sine. But if u equals sine, du is going to involve a cosine, which you don't see in the expression. So that's an indication that that's not going to be a useful u sub. And in fact, just looking at this integral, it's not very easy to understand how to do it. But using this formula will allow you to do that. So let's go ahead and do it. For item A, this graph up here it regards item B, so we'll go back to that later. Okay, so in A, we want to find the integral of cosine square, which according to the hint is equal to this expression, 1 minus cosine of 2x over 2. So what we're going to do here is, first of all, bring the 2 outside. And now this is just a u sub. We know how to integrate cosine. We know how to integrate 1. There's a 2x, that's a linear function of x. There's never any harm in letting that be your new variable u. So let's do u equals 2x, which means du dx is 2, and then du is equal to 2 dx. So how do we do this? There is no 2 dx in the integral, so I'm gonna make it appear and divide by another 2 outside. So the integral becomes 1 over 4, 1 minus cosine u du. What is this integral? 1 over 4. Integral of u, sorry, integral of 1 is u. And then minus cosine. What is the function whose derivative, or let's think about it this way. Leave the minus, and then you just have cosine. What is the function whose derivative is cosine? That would be sine. So u minus sine u. There are no endpoints because this is indefinite. But now you can go back and replace u with 2x. And plus c, because now this is the final expression, or at least you can simplify this like x over 2 minus sine of 2x over 4. And plus c. That's the integral of sine square. I'm just going to write similarly for cosine square, which was another one being asked in this problem in item A. Try that for yourself. But now we're going to move on to item B. I'm going to scroll up for us to see item B. Item B is, what is the area of the region indicated below? So below here, what we see is the graph of the function sine square. And there is an area between pi and 2 pi. So now we want to find integral between pi and 2 pi, sine square. This is we don't have to correct this with any minus sign in front, for example. The area is already above the x-axis. So the integral represents the area and not the negative of the area. Okay, how do we do this? So you can do the whole process again. Use u sub again. This time this is definite integral. So you do have the numbers. The u sub is the same, but now you do the process with the definite integral. Or you can just realize we've literally just computed the antiderivative. This is the function whose derivative is sine square. Now that we know it, we can just use it between the 2 points given, pi and 2 pi, and calculate this. So I'm going to do it this way because it's faster now. Now that you just found the antiderivative, use it. So what does this give you? You need to calculate this whole function at the number 2 pi. So that's what I'm doing here. Minus the whole function at the number pi. Use parentheses like this because the function itself has 2 pieces. But what does this give you eventually? The signs will all be 0. Sine of 2 pi, sine of 4 pi are 0. And just the 2 pi over 2 minus pi over 2 is just pi over 2. The value of that area. So I encourage you to now try to do this. Like forget about item A, forget we ever did that. Try to use the u sub again, the same u sub for this expression, but now you're going to need to change the endpoints. And you should still get the same answer, pi over 2. Okay, next one. What is the area function of the function below? So in this particular domain, this is just given for technical reasons. Forget about that. What is the area function starting at 0 of the function f, which is sine over cosine cube? So in other words, they want you to calculate the integral between 0 and x of the function f of t. sine of t over cosine cube of t dt. They want you to calculate this integral. It's going to depend on x, the answer that you find. Whatever you find is going to be a function of x. That is the area function. Notice that the area function is not the same thing as f of x. That is a prime, very different thing. We're not going to use that fact. This is true, a prime is f of x. That's the first form of the fundamental theorem of calculus, but that's not what they're asking. They want you to find the a function itself. So they want you to calculate this integral. How do we do this? This is a classical case of u sub with a fraction where you recognize that there is something in the denominator that you can call u, and you see its derivative in the numerator, or at least a multiple of its derivative. Namely, if you call cosine your u, what's going to happen? Du dt is minus sine, which means du is minus sine t dt. So we actually see a plus sine t dt up there. We can write a minus sign outside to make it minus. And that entire numerator now can get replaced with du, while the denominator is just u cubed, because it's cosine cubed. So always remember that when you're integrating fractions, if something in the denominator has its derivative in the numerator, or in this case a multiple of it, like a minus sign, or 2 times it, 1/2 times it, then that's a good candidate for u sub. All right, notice that I haven't changed the endpoints yet. Let's do that. So look back in the original endpoint when t is 0 and x. What happens to u? So u is just cosine of t. Cosine of 0 is 1. Cosine of x is cosine of x. Okay, endpoints change like this. Okay, so the integral that we have now, I'm going to rewrite, instead of 1 over u cubed, I'm going to say u to the minus 3. Because now it's clear that we can just use the power rule for this. Don't forget the minus outside. The integral is going to be u to the minus 2 over minus 2. Just add 1 to the exponent, but then also divided by that same thing. This has to be calculated between 1 and cosine x. So before calculating, I'm just going to cancel the minuses. This minus and that minus. You can just say 1/2 times u to the minus 2 calculated between 1 and cosine x. So it is going to be cosine x to the minus 2 minus 1 to the minus 2. Which is now, we can simplify this cosine square, 1 minus cosine square, which is sine square. And then sine square over cosine square is tangent square. That's the area function. Oddly enough, in this problem, it is a case of the final answer is a function of x, but there is no plus c, because once again, this is a definite integral. There were endpoints, right? So no plus c here. And ever since the beginning, I already told you we are looking for a function as the answer. This is the area function, a of x. So answer, a of x is equal to 1/2 tangent square x. At least one thing we can check about this, which is the fact that the area function that we were looking for started at 0, right? So a of 0 must be 0. What happens if you plug in x equals 0 here? An integral between 0 and 0 is just 0. So whatever function we found, at least at 0, it has to be 0. And that's true, right? Tangent square of 0 is 0. So we know that this has a chance to be working. This is a little check that we can do.